Hello, and welcome back to Learning with Lee. In today's episode, we are going to continue our discussion of how types are stored in memory by taking a look at how floats and doubles are stored in your computer. However, before we get into how they are stored, one thing you will have to understand in order to be able to understand the storage mechanism that is used for floats and doubles is what is known as scientific notation. And scientific notation is something that is used by scientists in order to allow you to determine how much precision and accuracy certain measurements that take place in the scientific world have. For example, let's take a look at a graduated cylinder, and my terrible drawing of a graduated cylinder, but let's just say you have a graduated cylinder with a certain amount of water in it, and out here you can go, okay, there might be, let's say these are hundreds of milliliters for the measurement here, so you got right around 440, 450 milliliters. So you might say, okay, I have 440 milliliters. Now what scientists care about is what are known as significant figures. So it's a matter of, do you know for certain that this one is accurate? Do you know for certain that this zero is accurate? Because normally zeros are considered not significant, they just are there to signify how large or small something is, such as in case it's 0 point and a whole bunch of zeros before some number, and we'll just go like that. These ones here really are only important to show you how small this number is. It doesn't necessarily say anything about the precision of the measurement. As a result of this problem, scientists came up with a certain notation in order to allow people who are reading their documents and their research in order to understand how precise their measurements were. So, to use our example of 440 milliliters up here, what you would do, you would go, okay, 4.4, and you would go times 10 to the second. And the whole reason that it's raised to the second is that that's the number of times you would need to move this decimal spot over in order to get 440, because usually the decimal spot would be right over there, but it would be this. And that lets you know that the 4 here is your final significant figure. You only have two significant figures. Now, it's fairly customary in scientific notation and the like that your final digit is an approximation in that it's within a certain amount of error. Typically, for something like this, it would be plus or minus 1. So it might be 4.3, it might be 4.5, but you're going with 4.4 because it's a good approximation. Now, let's say that you knew for a fact that it was 440 and the estimate was of the zero, because it might be 439, might be 441, but you know that it's right around 440 milliliters. So in that case, you would include this zero here, and it lets you know where the uncertainty in a measurement lies. The other major value that scientific notation has, aside from showing significant figures and uncertainty, happens to be in showing really large or really small numbers. For example, one of the common things you'll encounter in chemistry is Avogadro's number, which, as you'll typically see it, is 6.022. And while there's more to it, that's typically all that you'll need for your measurements, because usually your measurements are going to have less than 4 significant figures, times 10 to the 23rd. And that happens to be a good way of saying, I don't want to draw out 23, or more accurately, in this case here, because we're going to be taking 3 of these off like that, 20 zeros after 6022. And it also lets you not have to say exactly go, okay, which prefix do I use when I'm trying to describe something that's to the 23rd? Because it's well beyond millions and billions and trillions at that point. Now you might be wondering, what does all of this have to deal with how floats and doubles are stored? And the answer to that is that floats and doubles are stored using binary scientific notation. So it ends up being a bit interesting because you have to be willing to convert it into binary, then use scientific notation. First off, floats are 32 bits, doubles are 64 bits in general. And for floats, and we're just going to focus on floats here, for doubles you can pretty much extrapolate out and figure out how they're done. What you have is you have 1 bit that happens to be your sign bit. Then there are 8 bits that are used for the exponent of this, similar to how there's 10 to the 2 over here. This exponent here would be the equivalent of what this exponent here is, except since it's a binary scientific notation, rather than 10 to the 2, it would be 2 to the e that you have over there. There are a couple of oddities that deal with this exponent here. The first is that the exponent isn't a full unsigned int. It isn't 0 to 255. It's actually 1 to 254. So you can go 1 is less than or equal to e, which is less than or equal to 254. And the reason for this is that in case it's all zeros, meaning 0, or it's all ones, meaning 255, E has special meaning, and the double happens to represent something unique and special. We'll get into what that is in a little bit, but for now, there's this, and it's limited between 1 and 254. But there is one other oddity related to E that I want to talk about real quick, and that's that right now, if it's limited between 1 and 254, E can only be really large numbers and can only cause 2 to grow in one direction, basically moving 2 to the left and adding a whole bunch of zeros after it. Now, what if we want to represent a really small number, though? And that's something that people did, and that's because they ended up allowing you to effectively have it signed without having a sign bit. So what they did was they go, okay, E is actually, we then subtract 127 from it. So you can either get 2 to the negative 126, because the minimum E can be is 1, or you can end up having it be E to the 127. And anywhere in between there, obviously. But it allows you to end up actually doing this without having to store the sign of E in E itself. That's enough on the exponent for right now, and let's move on to what is remaining in this, because we've already taken a look at the exponent here, which corresponds to this here. We've taken a look at whether it can be negative or positive, with the sign bit up here, and the only thing remaining happens to be this section here, or what is known in this as the fraction. I'm not going to write all this out, because there's a whole bunch of zeros. For now, I'm just going to go, okay, we've got some zeros here. There's 23 of them total. That's what's important to remember about this, because right here's 9, and 32 minus 9, 23. Now, to take a closer look at the fraction, let's write out a fairly simple number in binary, so in scientific notation. So we'll just go with something like 1.01011. We'll go with times 2 to the 3. So what that'll do is it'll just say, okay, we need to move this over 3 spots to there for its new location. And what that'll do is it'll go, okay, how do I then figure out what this number is in decimal? And the answer is that it has to deal with the same way in which we were covering it before 2 episodes ago, where we were converting this. So this number here, you'd go, okay, this is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Now, what about these? As you can probably guess, since this number is decreasing the entire way, and this is 0, this is 2 to the negative 1, and this is 2 to the negative 2. And another way of looking at that is that this is 1 over 2, or 1/2, and this one here is 1 over 4, or a quarter. Then, in order to find our total number, we just sum all of these up along here. So we have 2 to the 3, or 8. We have 2 to the 1, or 2. And then we have 1/2 and a quarter, which gives us 10 3/4 for our final result of what this actually would be in decimal. Now, that's a bit odd because of the way in which this works, and that it goes, okay, quarter, eighth, etc., down that direction. And it also introduces one of the problems that exists in floats and doubles, and that is floating point precision. And by that I mean the fact that this fraction over here can only represent things as something divided by 2 to some power, which means that it really struggles with numbers such as 0.3 repeating, or a third. A third just is not cleanly representable in at least this form of float and double notation. There are ways in which you can do it in terms of saying, okay, I have some numerator represented by an int and I have some denominator represented by an int. But for this case here, this can lead to some weird stuff in which eventually you wind up with these errors due to rounding it to the nearest 2 to the somethingth at some point down along the line. Usually it's not a big deal, But when you're dealing with very fine precision stuff, and we're going to get into this once we get into stuff like graphing stuff, and let's say that I have some triangle here, and I'm going to want to see whether or not some ray from, say, this point here ends up being, and we'll just say that this ray goes off similar or parallel to this line here, and we want to see whether or not this intersects a vertex or if it intersects along one of these edges here, then there can be some serious issues in terms of rounding errors that go on and whether or not those actually impede our ability to perform math. And for those of you who watch something such as Far Lands or Bust, the reason why the ground shakes, such as in case you've seen it, you'll see like here's a block and its selection box is sort of off like this. That is because of this error that takes place here, in that as basically this decimal moves over 1, for every power of 2, one of these gets away. So the smallest then it can eventually represent is things like only a quarter of a block. And where Kurt currently is, it's probably down at, a 16th or a 32nd of a block, but that still is a noticeable difference when there's a 32nd of a block or a 16th of a block gap between where the game thinks it is and where a block is and where it actually is. So now that we have all this information, how do we combine all this in order to get something meaningful about how a float is stored? Well, the first thing that we'll look at is the sign bit. And the way this is represented mathematically, though it doesn't need to take place this way in your computer, it's easier to just have a logical statement of basically saying if it's 1 or it's 0, it's negative or it's positive. But you mathematically go, it's -1 to the sign bit. So in case your sign bit is 1, you have -1. In case it's 0, you have just 1. That gets multiplied by, and this is one of the weird oddities of this, is that this first 1 here is given to you for free. So you automatically have that 1 before your fraction, whatever your fraction may be. So if your fraction is all zeros, it still happens to have this 1 here, so you would have basically all zeros in case, let's say, you did that times 2 to the 1, so as you want to represent the number 2 in floating point notation. So this would be the number 2. But what you have here is then you have 2 to the exponent minus 127. So in case you happen to, say, want to actually have it be 2 to the 1, your exponent would actually be 128. But that's a relatively easy part of it. The weirder part is the fact that this 1 is already given to you. But thankfully, this is all stuff that your computer handles for you. It just is important to understand why certain errors that you will run into, especially when we get into graphic stuff like I mentioned, crop up due to how floating point numbers are stored. And basically, in case you go to a double, you can relatively easily take a guess at how this ends up being, is that you probably have a 16-bit exponent, and then rather than just having a 46, this is actually a 47, because it's not like you have to double the size of the sign bit. 47 bits for the fraction. So you can just fill in as needed, and then, of course, this has to scale appropriately in order to match the increased size of the exponent. But for floats that are 32 bits, this is the general way in which they happen to be expressed mathematically. And the other thing is to remember that this is in binary, so it's like 1.010001, etc., etc., etc. And then that gets multiplied by 2 to the something, so as that you can either move this decimal this direction, or you can move the decimal that direction, in order to get smaller or larger numbers. And with that, I would recommend spending a bit of time just working on this. Try translating a few numbers to the best of your ability from floating point notation back into decimal, and as well as vice versa. See that you can do it both ways. It'll be easier to start off from the binary, given this equation, and do it that way than it probably will be to go the other way. But spend some time just doing that to just understand how it works and be okay with it. This isn't something that we're going to have to deal with beyond this point. It just is, it's useful to know to understand why certain oddities in programming occur. So, thank you very much for watching. I hope you have a wonderful day.